Okay, so everything we have done so far has just been using the fact that we now know about cosec, sec, and cot. We're going to be adding some new identities into the mix, and these new identities are going to allow us to do more complex kinds of things. And then what we do after that is we add in some new identities, and then we add in some new identities again. So there's going to be a lot of things going on, and that's why it's important we try and keep up with all the new things that we have. So we know from year one, we call this the Pythagorean identity because it actually comes from a triangle where if the angle was x, this is cos x, this is sine x, and this is 1. It comes from a Pythagoras triangle like this, sine squared x plus cos squared x equals 1. But we're now going to try and create some new identities from this because we can take this identity and we can divide everything by cos squared x. And we're going to see what happens when we divide everything by cos squared x. And I'm just going to do each single piece divided by cos squared. So I'm going to divide this by cos squared x. I'm going to divide this by cos squared x. And I'm going to divide this by cos squared x. What do you think sine squared over cos squared is? It is tan squared. So we have tan squared x. Cos squared x over cos squared x is 1. And 1 over cos squared is sec squared x. Okay? 1 plus, well, tan squared x plus 1 equals sec squared x. But the most common way that I think you would see this, and you're going to be like, okay, but it's the same thing, is this. 1 plus tan squared x equals sec squared x. 1 plus tan squared is sec squared. And this needs to be memorized. You may have friends, cousins, siblings who have done A-level maths, and their teachers may not have told them to memorize this. But they will have been in the exam trying to remember what this is by doing a division, whereas if you can commit this to memory, you are going to feel more confident, and we will be using this again and again and again. You don't want to have to keep thinking of stuff. You want to be able to have stuff ready to go. You will learn later on that there is another relationship where you will see tan and sec popping up, and it's to do with differentiation and integration. Tan and sec have a differentiation and integration relationship as well. So it's nice that they kind of appear in this identity as well. You get 1 plus tan squared equals sec squared, okay? Right, we're going to have a look now at doing the same thing for this one, but we're going to this time divide everything by sine squared. So originally we have sine squared x plus cos squared x equals 1. I'm going to divide by sine squared, I'm going to divide by sine squared, and I'm going to divide by sine squared. So it becomes 1 plus cot squared x equals cosec squared x. And that one doesn't need any writing because it's in the right kind of way around of it just being a 1 plus. It just happens to be, if you asked any kind of mathematician or anyone doing A-level, we just always seem to remember this one as 1 plus tan squared is sec squared and 1 plus cot squared is cosec squared. It's just the way that we remember it, okay? So the three of them that we've got, there's sine squared plus cos squared is 1, 1 plus tan squared is sec squared, and 1 plus cot squared is cosec squared. Really, all 6 of them are being used. Sine and cos are being used in the first one, tan and sec are being used in the next one, and cot and cosec in the last one. You'll notice that you have the 1 plus with the tan squared and the 1 plus with the cot squared because there's a relationship between tan and cot. They're the same thing but the reciprocal. So that's why I see them as, oh yeah, I always know they go with the plus 1 just because if I know one of them goes with it, the other one will as well. And if you can remember that 1 plus tan squared is sec squared, well then 1 plus cot squared must be the only other thing that we haven't used, which is cosec squared. Obviously, you're going to look at them now and be like, how am I going to remember them? But we know with things, when we do lots more practice, we just start remembering things because we're using them so many times, okay? So we now are going to be expected to use all of these variations of things that we have, okay? We're going to do some proof questions, and we're going to do some equation questions, and then we're going to spend pretty much today's lesson working on all of those things, okay? So we are going to try and prove that cosec to the power of 4 theta minus cot to the power of 4 theta is 1 plus cos squared theta over 1 minus cos squared, whoops, that shouldn't say x. That should say theta. So can you just change that into your printout that it should say theta rather than x there, okay? Now, previously we had 2 tips, didn't we? And the 2 tips were change everything to sine and cos and combine stuff together. But it's not going to work for this, because if we change everything to sine and cos, what was the point in me teaching you about these identities that we've got here? So these are identities we kind of have to have ready to go, that if we ever spot them, we can use them. Now this thing that I've got on the left-hand side is not very nice, and I want to see how I can deal with this. I wrote 4 letters on the board earlier, and if you did hear what I said, don't tell me. Does anyone think they know what DOTS could stand for? Who wasn't here just at the beginning? Yeah? Were you here at the beginning? No. What do you think it is? Yeah, good. This stands for the difference of 2 squares. Difference of 2 squares, okay? Now, just as a reminder of the difference of 2 squared, if you had something like x squared minus y squared, that factorizes to x plus y, x minus y, where these things are the square root of this thing that you've got here. So as a bit of a challenge, if I had x to the power of 4 minus y to the power of 4 with a higher power, what do we think should be in the brackets for that? X what, sorry? X squared plus y squared, x squared minus y squared. And again, it's the same relationship. This is the square root of this thing. We've just halved the power for that. So although you can't really see it on first glance, this is actually a form of difference of 2 squares. And it is one of their favourite things to do in exams. As soon as you've got 2 things that are squares, or have been squared, and they're being subtracted, I would say 80% of the time, it's going to be a good idea to write it as a difference of 2 squares. So this isn't just like a random example that I'm showing you and you'll never have to see it again. This is something that is a technique that if you ever see 2 things that look like this, or even this, you want to think about how you can split them into 2 fractions. Motasim.
Does that only work for even numbered square, like even numbered powers?
So yes, because it doesn't only work for that. Technically, if you had x cubed minus y cubed, you could do x to the 3 over 2 plus y to the 3 over 2, x to the 3 over 2 minus y to the 3 over 2. However, these indices are so horrible to deal with that we don't ever use that. So it's only good, really, when the powers are even. Possible to do with odd, but not useful to do with odd. So a very, very good question. Thank you for asking that. Okay, so we're going to actually look at this thing that I've got on the left-hand side here, and we're going to just see what happens. So I have cosec to the power of 4 theta minus cot to the power of 4 theta, and we're going to do a difference of 2 squares on this. So the brackets should be cosec squared theta plus cot squared theta and cosec squared theta minus cot squared theta. Just get that first bit written down for me. If you've written it down already, think about why that's going to be important. Because I made such a big fuss about difference of 2 squares. What was the point? How has this helped? Anyone think they can see how this has helped?
Would you say that the cosec squared minus cot squared is equal to 1?
Good. So we should have remembered from the previous page, 1 plus cot squared theta is cosec squared theta. And I would have written this identity down if I was doing the exam here. I wouldn't have remembered all the variations of this one like we do with sine squared and cos squared. And when I'd see this, I would be like, okay, well, looks like I've got something to do with one of these. So I'm going to actually make cosec, I'm going to make 1 the subject, and I get cosec squared theta minus cot squared theta, which means that this second bracket that I have here is just a 1. So if it's just a 1, it's just cosec squared theta plus cot squared theta. So I just have cosec squared theta plus cot squared theta because I used the Pythagorean identity in a rearranged form to say that that thing there was 1. That's not meant to say 1 over, by the way. It's just saying that that thing is 1. And now what do you think we should do? Does the identity feel like it will be useful?
Doesn't cot squared theta equals cosec squared theta minus 1?
So yeah, we could do that actually. We could use the identity again, but I'm probably just going to go back to doing the previous tips that we had done before, okay? Because if we use that one again, we're just going to keep kind of getting stuck. We're never going to be able to get it to this stage that we have here. So I'm going to go back to what the 2 previous tips were, which was write them in terms of sine and cos, and then see what can happen. So we're still going to be using those previous tips. So cosec squared is 1 over sine squared, and cot squared is cos squared theta over sine squared theta. They have the same denominator, so I'm allowed to just add them together now, right? So that is going to be 1 plus cos squared theta over sine squared theta. Oh, it's so close. Is it the same thing, though? Because sine squared theta is 1 minus cos squared theta. So I get 1 plus cos squared theta all over 1 minus cos squared theta. And I think the reason they wanted it to end up looking like that is it looks kind of nice. Like, it does look nice. 1 plus something divided by 1 minus something. and then, yeah, what Chaz will do is he would cancel these out and he would do illegal maths and then he'd be thrown out of the class. But
I'm not doing it again.
well, you say you're not doing it again. I'm going to be watching everything you do now. So it's hard, but there was an extra step at the beginning where you had some stuff and it was like, okay, difference of 2 squares. Then you had to use the new identities. This isn't easy. But I'm hoping that even though you found the homework hard, it was easier than the first time you started doing it. Your brain was able to be quicker. And that's just a nice experience to remember that you get better at maths just by doing it and by practicing it. So has everyone got that written down? Is it okay for me to go on to the next bit? You nearly done, Harmon? Yeah. Okay. So now we're going to have a look at solving an equation as well. So I want to try and solve this equation, which is 4 cosec squared theta minus 9 equals cot theta. And we're in degrees this time because it says between 0 and 360 degrees. So I've written in that purple box, does this remind you of any equations that we've seen in year 1? Do you remember any equations that we'd seen in year 1 that were similar to this? I'll tell you what, I'll write an equation that's similar to it and see if we can remember how we dealt with it. So I might have had an equation like 4 sine squared theta minus 9 equals cos theta. Do you remember equations that we would have done like that? And how did we deal with this? What was the problem with this and how did we deal with this? Yeah, so the problem in this one is that we have a mixture of different trigs, okay? And the way we dealt with that was by replacing sine squared with 1 minus cos squared theta, so that we had an equation that was all in terms of cos theta and actually was a quadratic. So it's going to be the same thing for this kind of question, but we're going to replace cosec squared theta with the thing that it is linked to. So I don't remember the rearranged form. All I remember is that 1 plus cot squared theta is cosec squared theta. Great. So instead of cosec squared theta, I'm going to put in 1 plus cot squared theta. So that is going to be 4 lots of 1 plus cot squared theta minus 9 equals cot theta. So 4 plus 4 cot squared theta minus 9 equals cot theta. And then we're going to rearrange because the type of equation this is a quadratic. So I'm going to make it equal 0. So I have 4 cot squared theta minus cot theta minus 5 equals 0. And then I would go straight into my calculator to the polynomial solver. and I would put in that the A coefficient is 4, the B coefficient is -1, and the C coefficient is -5. And I'd like you to tell me what you get for the solutions for cot theta here.
5/4 and -1.
Good. So you get 5/4 and -1. Now what's the next thing we need to do to start solving these equations?
Reciprocal.
We take the reciprocal, because we can't do inverse cot, but we can do inverse tan. So I will take the inverse, sorry, not the inverse, the reciprocal of 5/4, which is 4/5. And I will take the reciprocal of -1, which is -1, okay? So I'm going to do these as two separate equations. Remember, we were in degrees mode, so I have a different calculator I'm a bit quicker on for this. So I'm going to put my calculator in degrees mode, and I'm going to do the inverse tan of 4/5. And we're going to just do that to one decimal place, which is 38.7 degrees. Next one is found by plus 180. So I get 218.7 degrees. No point in plussing 180 again, because it's going to go over the top. Okay, we'll do this time. Theta is the inverse tan of -1. Some of you can tell me the answer to that without a calculator, though. Yep, so it's -40. The calculator would give you 45, -45. But that's obviously not going to be in range. So the next one, when you add on 180, is the one that Sam gave us, which is 135 degrees. And then you can add on 180 one more time, and you get 315 degrees. Just make sure you eliminate the one that was originally given to you from the calculator, because it's out of range. So our answers are this, 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 and this. Do you want to see this on Desmos to see actually what's happened here? Because it's kind of nice just to see what happens. So 4 cosec squared theta minus 9 Desmos. Oh, they type it differently. They do it as cosec without all the extra letters in. 4 cosec said theta minus 9, and then cot theta. So these are the two graphs that we were trying to find out when they were equal to each other. I also better put it in degrees mode and make the x-axis go between, I don't know, 0 and 360. So the solutions are 38.7, which is correct, 135, 218.7, and 315. I typed in both sides of the equation. Cosec you have to type without the vowels. They just do it as a 3-letter thing here, okay? And it's just nice to think about what those graphs actually look like, okay? Everyone got that written down? So there is one question for you guys to have a go at here. And I'm going to give you like a few minutes to have a go at this question. If you're not sure, I will do this one slowly on the board, and you can ask me questions as I'm going. So it's radians mode this time. From the solutions to the equation. What did you get as the solutions?
I got minus.
Oh, yeah, yeah.
Because when you factorize it, it would be a plus, so it should just be a minus. Yeah, I'm going really fast. Don't compare what you're doing to what I'm doing. Okay, I'm just doing it so you can look at the answers afterwards. Yeah. Yeah. Yep. Okay. Okay, cool. That's good. Thank you. Yeah. Say that again. Oh, so this thing that I've got here is a quadratic equation, right? If it was a quadratic equation, it's x squared plus 3x plus 2 equals 0. Oh, I have done that. 2. 2 tan squared. 2 tan squared. 2 sec squared theta minus 2. I did include the 2. Yeah, I'm actually going to just do, we're probably going to pause on that second one. Because I've realised I've got too many equations and not enough provey questions. The proved ones look harder. So if you have finished that one, I'd like you to have a look at exercise 6D, and I want us to pick a question from that we'll do together, either from question 1 or question 6. Just do one that you think looks not very pleasant, and I'll see if we can use that as an extra example. And we'll do, because I've realised I haven't given us enough examples on this. Anything, we're going to pick a sub part of this, and I'll do a few of them as examples. So just whichever one you think looks. But that's the answers.
Oh, I was thinking, like, I was like, what? I was thinking.
Okay, so this equation that we did here, right? Hopefully you've nearly finished this. First of all, the reason I dealt with tan squared as the problem is because everything else was in terms of sec theta. So I replaced tan squared with sec squared theta minus 1, which was from the Pythagorean Identity. I then came up with this quadratic, and I solved the quadratic on the calculator to get the solutions were minus 1 and minus 2. I took the reciprocals, and then I solved the equation. Not easy, but a lot of work. It just takes time. Pardon? Yeah, I was actually I think I'll get us to do that question afterwards, because I've realised we don't have enough examples here that are like provey or like identity type questions. So from exercise 6D, from either question 1 or question 6, in fact from question 6, I'd like to pick 2 of them from question 6 that we will do together. as an example of some of these. So from exercise 6D, I'd like us to pick from question 6. I don't know, tell me like A, B, F, G, whichever one you think looks one that we should, a couple of them we should do, and you can see how I do them, and then that will give us a bit of a head start when we have a bit of practice for the rest of the lesson. E. Okay, so we'll look at exercise 6D, question 6E. And any other one that we'll do for the second one? I mean, they're all going to be good, so... Okay, and then we'll try G as well. So we'll try 6E and 6G. Now, 6E is this. So this is one, I'm sorry I haven't got this one printed in your booklets, but it's going to be worth just having a look at this one. You might like to write it down. So we're going to try and prove that 1 minus tan squared A over 1 plus tan squared A is equal to 1 minus 2 sine squared A. Now both sides look pretty difficult here, but there's going to be one side that is more linked to today's lesson. Which side do you think is going to be more linked to the new Pythagorean identities that we've learned? Pardon? The right side? No, I don't think this is going to be to do with it. I think this is the stuff that's going to be linked to the new stuff that we've got. So I'm going to use the identity. Can anybody remember the identity with tan off the top of their head? It's 1 plus tan squared x, which I'm now going to say is A, is equal to? Sec squared. Good. Yeah, that's okay, good. As long as we know that tan squared and sec squared are going together. So this is what they're going to ask. This is what they're trying to test it. Do you know these identities off by heart? If you didn't know these identities off by heart, I would look at this and be like, I don't know. I don't know what to do. Like, this looks really confusing. I don't know what I'm going to do here. But instead, I'm now going to try and use that identity. So that means 1 minus tan squared A over 1 plus tan squared A is going to be equal to 1 minus tan squared A all over, well, 1 plus tan squared is sec squared A. Now, if something is over sec squared, if it's the reciprocal of sec squared, what is the reciprocal of sec squared? Cos squared. So this is going to be a bit strange. You might think this is strange, but this is actually the same as this. Do you see how sec squared was in the denominator, which means it's a reciprocal? So I put it on the top, and I put it back to its other thing, which is cos squared. That's really, really useful. If you ever have something in the denominator that is one of the reciprocal trig functions, sec or cosec or cot, just pop it up to the top and put it back to the normal trig function that it is. Yeah?
Is it alright to change the A's into theta?
It is all right, but I would rather you do something that feels awkward now, because it then won't feel awkward in the future if you change if you always change them, you'll never get used to working in different letters, okay? And now we're going to just expand the brackets and see what happens. So I'll have cos squared A minus tan squared A cos squared A. So that's cos squared A minus, well, instead of writing tan squared A, we're now going to use some of those earlier tips that we had. What was one of the earlier tips that we should do with these questions? Write it in terms of sine and cos. So I'm going to have sine squared A divided by cos squared A times by cos squared A. Chaz, am I allowed to cancel anything out? You're not at this stage. Okay, don't worry. Am I allowed to cancel something out, guys? Yes. This, because this bit here, it's just to do with this, but I'm timesing it. I'm timesing it and dividing it, so I'm allowed to cancel this bit here and here, which is going to give me cos squared A minus sine squared A. I'm really, really, really close to this now. The problem.
How did you multiply 1 minus tan squared A and cos squared A?
So that was one of the things I said at this point. Sec squared is the reciprocal of cos, and it's already in the denominator. Right back on the very first page of your booklet, I said stuff like, hang on a second, why is my board going crazy? I said things like cos x is 1 over sec x, and I also said that sec x is 1 over cos x. So if this is something over sec squared x, it's like this. So I can replace this sec squared x with an up top cos squared. Okay? And what should I do for this last stage now? Because cos squared is 1 minus sine squared a minus another sine squared a. So I have got 1 minus 2 sine squared a. If you didn't use this identity to begin with, if you just decided to do the tip of changing everything to sine and cos, it would still have worked, okay? It would have just taken a bit longer. It would still have worked. But I would rather you try and spot the identities when you can do. Actually, I'll leave that there. I'm just going to scroll down a bit to do 6G. And then literally after this, it's going to be practice the whole lesson. So well done for listening to me, because I know it gets boring listening to me. So we have for 6, am I in a rush? Am I rushing you? Do I need to give you some time? Because I always rush. It's just what I'm like. This is going to be 6G. So I'm going to do cosec a sec squared a is equal to cosec a plus tan a sec a. Now I want you to know, when I, as a teacher, when I look at this, I don't see what is going to happen. I don't have this magic brain that is like, oh, cool, I know what I'm going to do. All I have is the same things at your disposal, which is the knowledge of the identities and the knowledge of fractions and how things are going to be added together. I don't have a magic power that sees what's going to happen next. Lots of other questions, I do have that magic power. But these kind of questions, I look at them, and I tell you what, as soon as I write it on the board, I feel a bit of a panic because I'm about to stand up in front of you all and try and answer this question. So I can imagine how it must feel for you and how hard this is, because it's hard for me as well, okay? But I'm going to start with this side over here, and I'm going to hope that something is going to happen. So, was there a question just then? Huh? What do you think I'm going to do with this? Good. Sec squared is 1 plus tan squared. The good thing about replacing that is, do you notice how this side is one single term that's all been multiplied? And this side is two separate terms with an addition. So if I introduce the sec squared as 1 plus tan squared, I'm going to be introducing two separate terms because of the plus. So I'm going to replace the sec squared with 1 plus tan squared a. And then I'm going to expand the brackets, which is cosec a plus cosec a tan squared a. I'm happy because this bit I've already got. So I'm not going to touch that thing again. I'm not going to do the thing that we did previously of trying to add them together, because that's a silly idea now. We don't want to add them together. We like them as two separate pieces. So what do I need to do? I just need to focus on this last bit and hope that it's the same as tan a sec a, which it is, but we're going to show why it is. So cosec a tan squared a, cosec is going to be, I think this is the way I would do this. I would say it's 1 over sine a multiplied by tan squared a, which is going to be sine squared a over cos squared a, like this. And so I can cancel the sine a with one of the sine squared. Agreed?
If you go from the first line to the second line.
From this line to this line.
First line to the
This is what the question is. That's the question, and this is me now this is what the question is, and this is me now working on the question. They asked me to prove that this is equal to this. So this has got nothing to do with this.
So it's tan squared a times cosec a sec a.
I'm confused what your question is, I'm sorry. I'm just going to continue this bit, and then Chaz, I'll come and talk to you about that in a second. So I can cancel now the sine a with the sine squared a. I can just remove the squared bit that I've got there. And I'm trying to show that this thing is the same as this thing, which I can see that it is, but I'm going to just make that super obvious. So that's cosec a. Combining these together, that is sine a over cos squared a. So that's cosec a plus. Now, I see this as a sine a over cos a with an extra cos a on the denominator. So the sine a over cos a is going to be the tan a, and the extra cos a on the denominator, well, remember, you can pull it from the denominator to the numerator and change it to sec a. which is the thing that we wanted to prove that it was equal to. We have now said that it is equal to this bit. We've got both of those bits correct. The thing that I think was confusing there, Chaz, is I was trying to prove that this was equal to this, but I'm actually starting off by saying this is equal to this, and then at the end, I've come up with the line that they wanted. Easy, right? Everyone looks really happy. Everyone looks like this is just going to be a breeze of a lesson now. So we've done some of I've done some of question 6 to give you a bit of a hint to see how I do things. You won't be able to do these things as like directly and quickly. You're going to have to try lots of more things out. But then I'm going to ask you probably to do the same questions again for homework, because you then know that you can do them and how you're going to approach it. If you want to, before you get started, there is another equation that you can do here, but there's going to be tons of these in the exercise. So my recommendation is just to get started on exercise 6D, but we're not going to do the beginning of exercise 6D. In fact, I want us to start, there's a few that I'm not very interested in. I'm not super interested in question 3, 4, and 5. So I'll tell you which ones to have a look at. And we're going to do